This is a problem that's quite similar to the first problem that we have solved for when we started with the induction topic, a bar sliding over two rails, essentially. But this time there are three bars, and all of them are moving. But the main difference of this problem from the previous ones is that there are actually two loops. So as a result, you need to compute the EMFs for these two loops. So let's just give the essential information. There's a magnetic field pointing out of the screen that's uniform. The rails have a distance of 4 meters from each other. And these two distances, 2 meters and 4 meters, are just the initial values. So we are going to find out that they don't have any importance at all. So I also do not want any time-dependent resistance. So as a result, I'm going to assume that these two rails have no resistance at all. So only the bars have resistances on them. And the question is to find the currents on each resistor. So let's start with basically with the final stage of the calculation, finding the current. So if you want to find the currents in this circuit, it's just like a usual DC problem. What do we need to do? So there's a loop with three resistors. There's a circuit with three resistors, but two loops. If you remember, when we are solving DC problems, DC circuit problems, there were actually two different approaches. I mean, you either satisfy the junction rule and then write down the loop rule, or you satisfy the loop rule and then write down the junction rule. So let's go ahead with the first one. So somehow we choose the current variables in here. So let's remember that we just choose them like that. So there's a current that's flowing on that loop essentially. Let's call this as IR, and that's the current flowing on that loop. Let me call this as IL. Right, so these are my two variables. What do they mean? What do these two variables mean? I'm basically superposing these two current flows. So as a result, on R3, the current is IR in the upward direction. On R2, the current is, let's say, in the downward direction. It is IR minus IL. It's just a superposition of these two values. And on R1, the current is, let me show it like that, is IL in the downward direction. All right. So as a result, in terms of two unknowns, I can express the currents in all branches. And at this point, of course, I can erase these variables that I have introduced. Right? Please remember the methods that we have used in there. So at this point, of course, we have just chosen these variables in such a way that the junction rule, Kirchhoff's junction rule, is already satisfied. We would like to express the loop rules. So I think I'm going to use this green color. So as a result, we have to choose two loops. And most of the time people use the same loops in here. So as a result, we have a right loop and a left loop. I'm going to use this R and L as the symbols for representing these two loops. For each of these loops, we write down the loop rule. Right? So the loop rule is essentially when you go around the loop, you just sum over all of the EMFs that you meet, and that's equal to the sum of the resistance multiplied with the current values. So let's just do it for this loop on the right side. So I don't know what the EMF is, so that's one of the things that we are going to find out. So, but this is going to, let's say, that gives us a sum which is I'm going to call as E sub R. And for writing R times I values, so I just noticed that when I'm going around this, along the direction of the loop, on R3 I'm going parallel with the current, so therefore I write plus R3 IR in here. On R2, I'm also going parallel with the current. let's say, parallel with the direction that I have written down the current. So therefore, this is plus R2 times the current on that branch. Right? So the only unknown in here is the resistance, and the other are the usual unknowns. So let's just then write down the same thing for the left loop. This is the loop rule. So again, there's a sum over the EMFs, so that's the thing that I don't know. And when I'm going on the loop, on R2, I'm moving opposite to the arrow that I have used to express the current. So therefore, I have a minus sign in here. So it's minus R2 times IR minus IL. And on R1, I'm moving in the same direction. So therefore, this thing has a positive sign. So this is plus R1IL. So these are my two equations. I need to solve them to find my unknowns. Unknowns are IR and IL. Once I find these unknowns, I would then complete the job that the question asks me to do, to find the current on each branch. So there are two unknowns with two equations, but of course, to be able to solve these equations, I also need to compute the EMF values in here, ER and EL. And for these, of course, I need to compute the EMF values when I go around that loop. So in any case, in the usual ordinary DC circuit problems, we usually had these well-defined EMF devices placed on the branches. Here we don't have it. And it appears that since we would like to solve these equations, we don't even need to know, we don't even need to place these EMF devices on branches, because the Faraday's law also already gives us the total EMF in here, right? So basically, there's an EMF associated with this right loop, let's say, where there's a well-defined area in here. It is that area. So the flux through that area changes. And so therefore, this rate of change of that flux is therefore should give me the EMF along that direction. So that's basically what ER is. So the important point in here is that even though in usual DC circuit problems we place the EMF devices at fixed places on the branches, here we cannot, actually we don't need to place the EMF devices in here. I just need to find the total EMF, and somehow Faraday's law gives me that value. Okay, so let's then compute the EMFs in here. So that was the picture that we had, but now the velocity values are written down. So let me write this thing down. So this distance, I'm going to call this as dr. Initially it was 4. Now you can see that distance is decreasing. I'm just going to be quick and write down the values in here. So that's minus 3t in meters, where t is in seconds. So when I'm writing numerical expressions for these functions, of course, I have to express which variable has which unit. So if time is expressed in seconds, then this expression is the value of that distance in meters. So this dl in here, that distance is initially was 2. This time I can see that this is increasing at a rate of 60. This is also similarly time is expressed in meters. So that distance, the length of the bars is L, so that's given as 4 meters. And there's a magnetic field, of course. There's a magnetic field pointing out of the screen, so that's given as 2.5 Tesla. Okay, so we start with the EMF in here on the right loop. For this one, of course, the enclosed area is this one. In any case, the corresponding area vector consistent with that choice is basically pointing out of the screen. So therefore, from here, we can write down the flux through that right part of the circuit is basically positive magnetic field multiplied with the area. Positive because the area and the magnetic field are in the same direction. Magnetic field is 2.5 Tesla. The area is equal to length times r, so the length is 4. This length of dr is 4 minus 3t. So you can see that this is 40 minus 30t, and the unit is Tesla meter squared. Okay, so that's basically the time dependence of the flux through the right loop. So let me just add a note in here. This Tesla meter squared unit. In SI, of course, we just also define this derived unit Weber. That's basically Weber. That's the same thing as Tesla meter squared. It's the unit of magnetic flux. So sometimes people also say that the Tesla unit, the magnetic field strength unit, is the flux density. So it's Weber per meter squared. But in any case, let's remember that the time derivative of the flux gives you the EMF, which has the unit of volts. So therefore, the flux unit also can be written as volts seconds. So sometimes you also see this unit used, but most of the time I'm going to use Tesla meter squared. All right, so let's then go to the flux on the right side. So in that case too, we have chosen the direction of the loop like that, and so therefore I'm measuring the EMF along that direction. So therefore, the area vector should be again pointing towards us. So let me put a vector in top of these. So these are the directions of the vectors. So the area is still parallel to the magnetic field, so therefore their dot product is still positive. So BAL is equal to 2.5 times 4 times 2 plus 6t. So that's going to give me 20 plus 60t. All right, so these are the flux values. So therefore, from here, we can compute the EMF. So I'll start with the EMF on the left branch, left side. So that's the negative of the time derivative of the flux. So that's basically minus 60 volts independent of time. So the EMF on the right loop is minus d phi r over dt. In that case, the time derivative is minus 30, so therefore this is plus 30 volts. Okay, so since I have chosen all the directions consistently with the right-hand rule, I don't need to check by using Lenz's law whether these signs are correct or not. So essentially, these are some numerical values that I have directly by applying the Faraday's law directly, I can compute both the magnitude and the signs as well. In any case, some people tend to, once they see this negative sign, they tend to change the direction in here. So they tend to change the direction and then express the EMF with a positive value. That's not really necessary because all of our equations are consistent with these signs. So as a result, if that sign doesn't bother you, it shouldn't bother you actually. So we can blindly use these values. So since when I'm writing down the loop rule equations, I have chosen the directions like that to express the EMFs along that direction, I'm going to use these values. So let's remember again, left EMF is minus 60 volts, right EMF is plus 30 volts. So these are the things that I'm going to use. So let me write plus 30 volts in here and minus 60 volts for the other one. Okay, so at this point I'm just going to write down the equation. So the first equation is this, plus 30 is equal to the resistance values R3 and R2 are both 3. So therefore, if I cancel the 3's, I get like 10 is equal to 2IR minus IL. So that's my first equation, written in terms of the unknowns only. So the second equation is this. It is minus 60. That's equal to, I get minus 3 in here, IR minus IL. And then R1 was 1 ohms, so I get plus IL. So that's going to give me minus 3 IR plus 4 IL, and that's minus 60. So there's nothing that I can simply cancel. All right, so what I'm going to do in here, let me just write down these equations in here on the left side. So I'm going to write them down. Right, so we have two equations with two unknowns. How do I solve these usually? I just multiply these equations with some numbers and add them up so that I can cancel some of these unknowns. So to eliminate IL from these equations, I multiply the first equation by 4, second equation by 1, and add them up. So what do I get? On the left hand side, I get 40 minus 60 minus 20. On the right hand side, I get 8 minus 3 is 5 IR. So from this, we get IR to be equal to minus 4 amperes. Okay. So I then erase in here because I don't have much space. So I multiply. I can do the same thing, or I can just insert this into one of these equations and solve for IL. But I'm just going to do it like that. So I multiply the first equation by 3 and the second equation by 2 and add them up. So 30 minus 120 is minus 90. And on the right, I get 5 IL again. So from here, we get IL to be equal to minus 18 amperes. And therefore, IR minus IL, that's the current in the mid-branch, that's therefore equal to plus 14 amperes. Again, two of the currents are negative, but I don't get disturbed by this fact. Doesn't matter. That's not that important in here. So as a result, I'm going to say this. So therefore, on R3, the current in the upward direction is equal to, let me erase this part so that I can write this thing down clearly. So that part is not there. So this IR is equal to minus 4 amperes. So there is a current flowing in the upward direction, which is minus 4 amperes. On the resistor R2, the current flowing down is plus 14 amperes. And on the resistor on the left side, the current flowing down is minus 18 amperes. If you're not comfortable with this and you insist on expressing all the currents with positive values, then let's also write them down in a corner like that. So I'm just going to quickly draw the picture like this. So as a result, let me use a blue color for this one. So in the mid branch, the current is 14 amperes going down. So therefore on the right branch, the current is going down, which is plus 4 amperes. And on the left branch, I have a current which is flowing upward, which is 18 amperes.